Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the Zurich Instrument MFIA, which is an impedance analyzer and a pretty sophisticated one at that. But it's actually a lot more than that because underneath it, it's built on a lock-in amplifier. So this is a long video with a lot of discussions on how this thing works and a lot of different experiments. And I really hope that you find them useful. In the description, there is links you can jump to different places of the unit. There's so much to show about this because it is sophisticated and complex underneath, and I really want to make sure we understand how it works. So let's get started. Now, as is customary on the Signal Path, every review is also an opportunity to learn about the instrument, its fundamental operation, and the many applications it can have. So we need to understand how it works at least so we can take the most out of it. So bear with me as I go through some of the critical information. So lock-in amplifiers really excel when you have signal-to-noise ratio limitation. Now, in general, when you want to measure a signal, especially near DC, you want to move it away from the DC as soon as possible. And that's because any amplification near DC is going to be subject to the 1/f noise of any amplifier that you use, which is going to bury you in the noise even more. At the same time, you have all of these power line coupling and other harmonics and junk in the spectrum, particularly from ground loops, that are going to make it even more difficult to process that signal near DC. So the main idea of a lock-in amplifier is pretty simple. Use coherent up and down conversion so that you don't have to keep your signal at DC when you're performing any kind of computation on it. And that's the main idea here, shown in this case an optical experiment, but it doesn't really matter. It doesn't have to be an optical experiment. Any signal that comes in, you can use a modulator to modulate that with your frequency of choice, in this case a sine generator. Now, once that signal is processed and multiplied, you now have the signal Vs of t, which is modulated with Vr of t, and is no longer sitting near DC. Is sitting somewhere out here, and therefore now you can amplify it and process it, and you're not subject to the 1/f noise and everything else that is dominant at the lower frequencies. And then you use exactly the same signal Vr of t to now down convert your signal back to DC. The advantage is that this is a coherent up and down conversion. Now, a few other things happen at the same time. Anything that's not coherently modulated with Vr of t will be inherently rejected because it's no longer correlated to the signal Vr of t, and then you have all of those additional advantages of rejecting everything that's not related, environmental effects and drifts that are not part of your system or other interfering signals. And then once you come out, then you get your signal and the angle of the signal depending on the phase difference between the signal that has arrived into here versus the reference, and then you get all the information from that. You get IQ down conversion essentially. Now, things become interesting when you start comparing an analog versus a digital lock-in amplifier. In an analog lock-in amplifier, you basically process the entire signal in an analog domain. You have the input coming in, which has the modulation. You amplify it over here, away from the 1/f noise, and then you use a mixer to down convert it, and then you have further amplification now that the signal is large enough to condition it to the range you want, and then you put that out. So over here now you can put an ADC, you can digitize it, or you can visualize it in any other way that you want. This is how lock-in amplifiers were built before sophisticated ADCs and DACs were available. Now you can do something more interesting. You can have an A to D converter with a really good dynamic range and a high number of bits, more than 12 bits for example, and now you have an input amplifier that needs to condition that to the right input signal range of the ADC. After this entire thing is in the digital domain. So all the multiplication, processing, filtering can now happen afterwards as long as you condition this signal cleverly to take the most out of the front end of the lock-in amplifier. And then you can put that signal into a DAC and bring an analog signal back out again, which then becomes similar to how this signal would look like. And you can do other things. And of course, once you're in the digital domain, you can throw some pretty sophisticated DSP at it. And because you have this ADC that has a certain bandwidth, you can look beyond the DC down conversion also. You can actually perform Fourier transform on the down converted signal and see all these other interesting effects, some of which I will show in our experiments. You do have to be careful in how you define the input sensitivity of the instrument in this case, because this input amplifier has to always place a signal within the optimum input signal range of the ADC. All ADCs have an optimum input that you need to feed them to take the most out of their spurious feed dynamic range and the number of bits they have available. And that's one of the things that's available to see in details in the documentation of this instrument too. Now, there is another really subtle aspect to the filtering that's worth paying attention to, and that's the ability to do sync filtering at the output of the ADC, and that's something that this instrument is capable of. This comes up when your modulated signal is already at a very low frequency. For example, let's say you're doing something at 30 hertz. In order to really cut out everything that you don't want, you now have to have a low-pass filter that can cut off at 30 hertz, which means that you would have to record for a very long time. In order to avoid that and get a faster response, what you could do is you could create a sync filter that will filter out strategically the modulated signal and its harmonics. And this comes up because of the imperfections of the system, harmonic generation inside of the demodulators, and some other DC offsets. And that would be very hard to remove with a low-pass filter. And by applying a sync filter already built into the instrument, you can have some really high rejection in these key places. And there's a good example of that. Here's a signal that's been modulated at 30 hertz. This is the signal we're actually interested in. Now imagine if I want to filter this thing out using just a regular low-pass filter. I would have to have the low-pass filter come all the way down here, which is really hard to do and it would take a very long time. But by applying the sync filter, you can null these modulation frequencies at 30 hertz and twice the 30 hertz. Now you don't need to have to wait for such a long time. It's a really subtle point, but it's good to know about it. And now we can finally talk about the block diagram of this instrument. And look at it, it's beautiful. There's so much stuff in here and so many capabilities that it would take hours and hours just to figure out all the ways you can reroute signal inside of this thing. So what's the very first thing we need? Well, we need to get signals from the outside. And we know that we need to digitize them and amplify them as soon as possible so that everything else can happen in DSP. So here we have our front panel inputs. There's two ways to input the signal into the instrument. You can input them as voltage, or you can input it as current, and then a transimpedance amplifier will condition that and amplify it before it goes into the ADC. And here's our ADCs. We have two of them. These are running at 16 megasample per second, 16-bit ADCs, and each of them in the front have a low-pass filter at 10 megahertz, which is an anti-aliasing filter, and it blocks out everything else after it. So they have quite a bit of oversampling on top of that. And all of this determines the input performance of the instrument. So this is a pretty critical part, and all the overload detection and input range amplification, all of that has to happen here. Once you're at this point, you're in the digital domain, and now you can do all your modulators and demodulators in DSP. Now at the same time, we do have a whole bunch of auxiliary signals as well that we can use. We have the signal outputs so that you can put the signal back into another instrument, and this is equipped with also 16 megasample per second DACs in this case, and this I think should say output range amplifier, not input, and you can use those and reroute signal into them as you want. For the auxiliary inputs and outputs, you have now 16-bit 15 megasample per second ADCs for the auxiliary inputs, and on the auxiliary output side you have 4 DACs, each of them running at 612 kilosample, but these are now 18-bit signals with the appropriate filtering and everything. So this is your analog domain. Everything on the left side is your interface to the physical world. Whatever you want to do in and out, you have to manage it from this side. At this point on, everything is in the digital domain. Now at the heart of the DSP, there are actually 4 demodulators and oscillators. One of them is enabled by default, and here's your oscillator over here, which you can use to apply signal to whatever device you want outside. And then you have your down converter, low pass filtering with a phase shifter as your demodulator. And with the option, you can unlock the other 3, which are down here, and you'll end up with 4 of them. Now think about what that means. It means you have 4 independent phase shifters and oscillators, and demodulators, you can run 4 lock-in amplifiers in parallel at different frequencies and look at harmonics. It just grows exponentially in complexity and capability because of that. There's also a 5 megahertz extension, which we have on this unit, and there's even a PID controller and PLL controller, which then opens this up into real-time closed-loop systems, which I'll try to make a video about at a later point, but really cool stuff you can do with this. The sweeper and FFT and scope visualizers are there, one with segmented memory, and there's also a spectrum analyzer function with a 58 kilohertz span, which allows you to visualize the spectrum beyond the fundamental signal you're looking for, and that opens up a whole bunch of interesting things too. We'll do an experiment on that. Now, in order to connect to this, you connect typically with a gigabit Ethernet, which is what I'll be doing, and there's also USB interfaces as well. You have a whole bunch of trigger inputs for synchronizing things from the outside, and a digital I/O, which you can use for additional things in your setup. Of course, we should have a clock in and out, which we do, which is a 10 megahertz input and output, which you can then use a very, very precise and accurate 10 megahertz input if you're looking for making very absolute accurate measurements in frequency with, of course, its own PLL. So look at all of this that's there. And of course, managing all of this has to happen inside of their software, which we will talk about in detail too. For completeness, it's important to appreciate the input voltage and current noise density of the instrument as an overall system, basically at the input ports of the unit. When the input voltage range is set to about 1 millivolt, once you're past around 20 hertz or so, you're sitting at 2 nanovolts per square root hertz, which is pretty good. And of course, 1 over f takes over as you go lower in frequency, so you definitely want to be further away from it if possible. Once you're at the 3 volt range, of course, the noise goes up, but your signal to noise ratio should be higher at that point anyway. That's why you're using the 3 volt range. At the same time, this shows how important it is to pick the right input range for your instrument. This is true for any instrument to maximize your dynamic range. For the current input, with the TIA set to your 1 nanoamp range, you're looking at around 10 femtoamp per square root hertz, which is also pretty good. The bandwidth is less, of course, once you have more and more gain. It extends beyond that, and then you get more noise as you increase the input current. On the output side, you have the opposite situation where the DACs are generating these signals and then amplifying them, and often you can use this for your own modulated signal, so it's important to look at this performance too. We do have a different set of ranges over here, and you can see the noise performance, and the phase noise is pretty good. I mean, out here at 10 to the 5 hertz offset, you're sitting at minus 155 dBc per hertz, and that's sometimes important in some applications once you're beyond the coherent length, but typically it doesn't really pose major problems. And now finally we get to a point where we can appreciate how we can use the lock-in amplifier to perform impedance measurements and what the advantages are. So we know that we have oscillators available. We can control the amplitude, the frequency, and the phase of those oscillators. Now imagine we apply that signal to some kind of a passive network, an LCR network of some kind. And then we look at how the signal changes as it goes through that network by measuring it on the other side using our input ports, the lock-in amplifier. And since everything is coherent, we can compute the angle and the amplitude, and from that we can get the exact impedance. And that's basically how this thing works. We do have our drive voltage. That drive voltage is now coming from the oscillators, and we can perform the voltage measurements and the current measurements and get the impedance. So now we can actually label our lock-in amplifiers with the typical HL port naming convention that impedance analyzers have. And this is a 4-port measurement, 4-wire measurement. You can also do a 2-wire version where you take what your drive voltage is as your input and then the current measurement to get your output. So if you notice, this doesn't use a bridge, and because it doesn't use a bridge, it's fundamentally different from a typical LCR meter. It can go to much lower frequencies faster, and it can also measure significantly higher impedances into the tens of gigaohms, which LCR meters cannot do. There are of course disadvantages too with this approach, but it's a matter of what is more important in terms of measurement. And you can do all your typical compensation techniques exactly the same because everything is now happening in software. You can remove your shorts and opens and everything else in order to ultimately measure your DUT. This is a beautiful abstraction wrapped around the lock-in amplifier. So it removes all that complexity from you. You just think about this like an impedance analyzer at this point. So how well does all of this work as an LCR meter? Well, surprisingly well given the quality of the input-output interfaces and the data converters that are built inside of the unit. So at the bottom here on the x-axis we have frequency of measurement, which goes up to 5 megahertz, and then on the vertical axis we have the absolute impedance value. And then we have surfaces that tell you the absolute accuracy that you can expect. So we are in the 0.05% accuracy for impedances from 1 to 1 megaohm and of frequencies that approach almost 1 megahertz. So we're dealing with a very good LCR meter in its own right, and it's going to be able to do these measurements extremely quickly. And as you go further away from that, as the impedances go higher and higher, you're going to have reduced absolute accuracy. But I mean, look at this. We're sitting at above 10 gigaohm, and we can get 1% absolute accuracy, which is very good. It's not something you can typically get from every LCR meter. And then in terms of the phase accuracy, down to 2 millidegrees sitting here in the middle, which is also very good. Of course, phase accuracy itself translates to impedance accuracy as well. And if you're interested in measuring quality factors, measuring quality factors over 100,000 should not be an issue given, again, the dynamic range the instrument has and the ability to measure extremely high impedances, again, sets it apart as a typical LCR meter. So I'm eager to try it out as an LCR meter, but there's all this information so you can make sure that it definitely fits your needs. Also keep in mind that there are disadvantages in using a lock-in amplifier as an impedance analyzer because generally the inputs and outputs of a lock-in amplifier are not optimized for very high voltages and for very high currents. So if you want to measure up to 40 volt DC, for example, you cannot do that with this instrument. It's limited to 10 volts. Or if you need to push a lot of current into an inductor to examine saturations of the magnetic core, you cannot do this with this instrument because it can only go about 10 milliamp or so. So you have to look and see what kind of measurement setup you actually need, and of course take cost into account. And here's the front panel of the Zurich Instrument MFIA. And even though they're part of Roden Shores, I really hope that they keep their logo because it's really neat. At the front, you will see the familiar H and L ports used for LCR meters, and the spacing is compatible with all LCR fixtures. It's an industry standard. But in reality, the L and H ports are just inputs and outputs of the lock-in amplifier, as we saw before. We have our TIA current input, and we have a differential or single-ended voltage input. And the signal output side can also be differential or single-ended. There are LEDs indicating the enable-disable status as well as overload conditions on these visually, which I find also is very helpful. At the same time, we have 2 ports for auxiliary input and the 4 ports of the auxiliary output, and the light here indicating the status of the instrument. That's it, pretty straightforward. And in the back of the unit, we have a few additional ports. We do have the option of running the unit from a 12-volt DC input, but there's also the AC line with a hard switch. And thanks for including this. It's always annoying when you have to look for the adapter to run these things. We do have our trigger input, trigger output, 2 of each, and the clock input and output at 10 megahertz. Gigabit Ethernet, and USB device and host, and the 32-bit DIO that we saw, which is 3.3 volt TTL compatible. There is also a Wi-Fi card in here, but I don't really recommend using that, especially if you have multiple of these. Wi-Fi isn't great for streaming things that are short messages. But yeah, pretty straightforward also. So let's take a look inside of this instrument. Now, despite the fact that it's super compact, the main power supply is not part of the main board neither, which makes sense. You don't want the switching noise of this anywhere near those sensitive devices. It's sitting kind of its own Faraday cage. Simple isolated power supply with a single 12-volt output. I bet you I can remove all of this and actually put a battery pack in here and run the whole thing internally. This is why it is easy to run it from a 12-volt DC source as well, because you're just simply replacing this. The thermal solution blows air into the board, and it brings air from the side of the instrument and out of the back of the unit, and it seems to work reasonably well as well. Of course, we can't see any of the good stuff. We need to remove this. And when you remove the next cover, you will see the main PCB, which is both impressive and surprising, because they've managed to get away with creating only a single PCB to handle everything. That includes power supply, all the mixed mode signals, all the sensitive input, as well as the digital activity that's on here. Testament to the good isolation and design they've managed to achieve. So here's all the power supply section. You can see them all over here at the bottom, and there are even pads for putting cages around these, especially the switching devices with all the inductors, but apparently they don't need them because they haven't been populated at all. Now we have the sensitive inputs over here, and you can see that there is indeed a separation between these two, and there was some cages on top of these and have removed the covers. Luckily they are not soldered onto the board, so they're easy to remove so you can see what's underneath them. 2 sections over here, one over here for the current input and one over here for the differential voltage input. Then we have the outputs. These are the signals leaving the instrument, and all of the auxiliary additional IOs that are available. The signal path, pun intended, of all this can be easily traced, but I really like the compactness and the way they put this together. This device over here, most likely an embedded computer module that basically handles all the servers, all the internal running, and the firmware operating system that's running on here. And this is most likely an FPGA that handles all the computation. There's some memory also next to it, a whole bunch of other auxiliary circuitry here, nothing interesting, and the battery. But let's take a look at some of the component choices they have here to handle the input and the outputs. If you think about the inputs and outputs of this instrument, in many ways they're going to resemble the input and outputs of oscilloscopes and arbitrary waveform generators, because you're reconditioning a signal before they arrive at data converters. At the same time, here you have much more stringent linearity and noise requirements because you're using data converters with many more bits, and you want to maintain that sensitivity at the input, which is nice to see. Now at the same time, we see a whole bunch of different relays. These relays are used for range switching and path switching and enabling and disabling single-ended differential inputs, for example, and this is also quite common. Relays are slower, more expensive in some ways, but they'll provide very good repeatability and very good protection, and are of course completely linear. So the very first thing we notice is that if this is a differential voltage input, there's a bit of an axis of symmetry right over here. It looks like some input protection, but the very first circuit that is seen at the front is actually a pair of matched JFET inputs. And these are ultra low noise, 1.6 nanovolts per square root hertz at 1 kilohertz, and they're from a linear systems. So it makes sense to see something like this as the very first thing you have to apply your signal to, and that provides you the input impedance and of course the noise that you would expect. And once you construct your differential pair using those JFETs, then you can recondition the signal, put some op-amps and everything else afterwards, and then we arrive to our first data converter. And if you notice, there is an equivalent one, a similar one, at the top as well. So you have 2 identical ADCs. The difference is that at the top we have a current input path. So you have, instead of a differential input voltage amplifier, you have a transimpedance amplifier that's constructed using the front-end devices, and that signal also arrives at the data converters. So this two paths essentially get digitized in an identical way, except here we have voltage single-ended to differential, and at the top we have a transimpedance path. And these are 16-bit digitizers up to 125 megasample per second, but they're, I think, running at a little bit lower clock rate. Now, everything in here, all the DACs and ADCs at FPGAs, they all need to be clocked in some way, and they need to be clocked synchronous and perhaps with some phase adjustments between them. And for that, they're using this Texas Instrument device here in the middle, which is a precision clock conditioner with an integrated VCO and PLL. So you basically give it a reference signal, and you run the PLL, and that PLL can then be sent to many devices at the multiple frequencies, and you can then even adjust the delay between them. So this guy drives this ADC and this ADC, and it drives this DAC and everything else that's down here, as well as providing clock to FPGAs and other things. Very cool little component, clearly designed to bring many systems with clock requirements together. And we have a pair of low noise LDOs here to separate the power supply of our data converters from everything else to provide a really good power supply rejection so that they perform at their best. And then looking at the transmit path, the opposite happens. We do have a DAC over here. This is also from Analog Devices, 12, 14, or 16-bit 500 megasample per second DAC. This is a dual DAC. We see it in all kind of arbitrary waveform generators, and that signal is reconditioned, and at the very end is fed into a pair of current feedback amplifiers, which then provides you this nice drive to the outside into a 50 ohm environment, which is nice to see how they tie all of these together. Architecturally, it's simple, but of course the elegance is in the design and making sure that these things perform at their best. And on the auxiliary inputs and outputs, we're going to need similarly ADCs and DACs, and we can see a whole bunch of them here. There's another ADC over here. This is also 16-bit, running at somewhat of a lower rate. We have a pair of 18-bit current output DACs to provide the DC voltages, and a whole bunch of delta sigma ADCs scattered all over the place. These are lower rate ones again, but also at 16 bits. So tons and tons of signal conditioning and mixed signal design going all over this is really quite impressive. These bigger chips that you see are just IO expanders, and not surprising to have them because you have to control all of these relays. So it makes sense to just batch them together and just have a single serial IO that can control all these relays at the same time. Really beautiful and compact design overall here. And there is a cutout in the board actually. I forget exactly where it is. It's in the inner layers to separate the power supplies and the analog signals from the digital side. Lots of work must have gone through this. And this looks like it is revision 1.7. Yeah, beautiful work. And the next most important part of this instrument is going to be the software, because it's the only way to really interact with the unit given that it does not have its own display. And this is Lab 1, a unified platform that Zurich Instruments uses to control all of their products. Now, I've been using this software for about 6 months now, and I am genuinely impressed. Not only has it been written from the ground up by people who understand their instrument, but they're also passionate about building complex setups and know how to build software systems together. This is essentially a web server, and it runs in your browser. As a result, it is completely scalable and can control as many of their instruments as you want, and you can control it pretty much from anywhere. Now, depending on the instrument you connect, the different buttons on the left will be the capabilities of this particular unit. Now, this one has all the options, so there's a lot you can do. At first, this is almost overwhelming because there is so many things you can build. You can build your own lab in almost any configuration that you want, and nothing is really hidden. They treat you like real engineers. So there's a bit of a learning curve at the beginning, but once you catch on, the design language and how you use it is consistent from beginning to the end, which is a hard thing to do when there's so much flexibility. And we talked about how this is an impedance analyzer that's wrapped around the lock-in amplifier at its core. So when you first start it, you get the impedance analyzer window, and it has all the familiar settings that you would expect from an LCR meter. For example, in this case, we're measuring RS plus CS, so basically a capacitance and the equivalent series resistance along with it. And we're making a 4-terminal measurement, and the diagram on how to connect that to the unit is also shown up here. So as a result, you don't have to worry about what's going on underneath anymore. You can use it like a basic LCR meter. And all of the parameters are measured over here, and we have a numeric display which can be enabled by clicking numeric over here, and you get some of these parameters now shown in large font here. Now at the same time, here at the bottom there's a scale that shows you where you're sitting within that scale. So for example, we're measuring over here the series resistance, 6.2 ohms. I have something connected to the front of the unit, and that 6.2 ohms shows up over here. Now if that parameter varies a lot, this line would move around and it will leave a trail behind it, and so immediately you can see how uncertain that measurement is. Kind of gives you the distribution over there, which is a nice touch that they have added there. Anything you hover over will give you a help of what that parameter is. You can see the path in the API, so you can see exactly how that parameter is controlled. And if you change anything, at the very bottom, the command that was used to make that change shows up. In fact, if you click on the API log, you can see everything that was done in order to achieve that particular lab setting that you see in the software. So you can very quickly develop your own code. It's just so much in there. They really clearly thought about how to put this thing together. And as you can see, it is running in a browser. I'm just simply full window so we can take a look at it. So let's connect a few devices and play around with the GUI and familiarize ourselves with how it works. Now, we talked about how the front panel spacing of the connector allows this instrument to be used with a wide range of LCR accessories, but Zurich Instrument also makes one of their own, which is this little unit, and it's really high quality. The whole thing is metal, even the tabs, and at the back of it, you get access to the signals that come out of the unit. This is the MFITF. They really love their acronyms. So this allows you to connect this to the unit, calibrate this, and this interface over here is now 0.1-inch header, so you can build really inexpensive fixtures that fit into this. In fact, this kit comes with a whole bunch of them, including shorts and opens, so that you can do a calibration, and then you can add whatever you want. So here I have a little tiny capacitor added to it. There are surface mounts versions of it, but of course you can make your own version of this, because once you calibrate, this becomes essentially a consumable to be used with this. I really like this idea, and I've been using it a lot in the past 6 months. So the very first thing to do is to calibrate the instrument to get rid of the fixture effects as well as any of the parasitics. And this unit offers a wide range of calibration possibilities. In this case, I'm going to do a short and an open. And once you select that, you just have to insert the short open standards. In fact, if you look over here, I have already inserted, for example, the short in this case. So we will do a short calibration and we will sweep the entire frequency range. And the nice thing here is that depending on the number of points you enter and the frequency range, you can then later on change your operating points, and it wouldn't matter because it has that calibration information. This is quite common for our LCR meters. I won't bore you with the details. I'll just run through the calibration. And the short calibration is done, and you can see it tells you what was measured and what was subtracted. So we did have minus 150 microohm of resistance, probably due to some of the metal connections on top of each other, but that's been removed, and of course some series inductance. Then we'll do the same thing with the open. And now with the full calibration, I have inserted a new device into the fixture. This is supposed to be a 1 picofarad through-hole capacitor, ceramic. Now, of course, with 1 picofarad, even the leads and the distances between them and how they're soldered is going to affect the total parallel capacitance by hundreds of femtofarad, not to mention that this is not a very good capacitor. Now, we measure this here in the instrument using the very high measurement precision so that the measurement's more stable, and we're measuring 1.19 picofarad. That's quite a bit off from the 1 picofarad it should be, and I verified that this is indeed the correct value using a different LCR meter, and that tells you the importance of being able to solder something onto the board and the parasitics that come with it. This is why normally people don't make through-hole capacitors of this value anymore. Now, having said that, we can also set the test signal that's applied to the capacitor and the frequency. And this frequency should be well within the self-resonance frequency of this capacitor. And that's the case because if you look at the phase, we're sitting at minus 89.9 degree, which is well within where it should be. This is a good capacitor at this frequency. Now, at the same time, we get a whole bunch of other parameters being extracted at the same time. From this, the model of RP in parallel with CP has been created. And the parallel resistance is, in the orders of a gigaohm. And that makes sense because this is a ceramic capacitor, it's tiny, it doesn't have a lot of leakage through it. But if you look at the measurement here, you can see how much uncertainty there is. And that smearing across tells you the big variation across the measurement of this capacitor. But if you look at the actual capacitance or the phase, we don't have that because there's a lot more confidence in this measurement. Now you can add almost anything to this numeric display. Any parameter that's available internally into the instrument can be extracted. So here on the tree, you can see if I extract this with impedance 1, you can extract it again. All these parameters can be brought in here. So for example, bias voltage, I can turn the bias voltage on. There is no bias voltage here, so it's set to 0, and it all makes sense. Now at the same time, you can also create a second impedance analyzer. This is now disabled. You can enable it, so you can go back and forth between two different setups and very quickly compare things, and without having to make all the values changes. It's really, really well thought out. So the bias voltage is at 0. What if we add some bias and see what happens? Well, I can go under advanced, and here right away I will have control over the bias voltage and a whole bunch of other parameters. Now, a few things to note. For instance, if you look at the input monitor, the input monitor tells you the range of the signal arriving at the voltage and the current inputs and where they are with respect to the range that they selected. So this is a tiny capacitor, so there's a very small line in the middle because you have a huge range left over. And the range is right now set to automatic. And the test signal is also setting the range to automatic because it's only 300 millivolt, and we do have a huge range here available for us. Now I can add a bias. Let's go and enable the bias over here. And we can enter 1 here, which will become 1000. So now we're applying a 1 volt offset to the output. But if you pay attention at the bottom right here, we do get this red line. And this is a very helpful feature because it tells you if any of the signals that the input and output are overloaded or have been overloaded in the past. So you can immediately address it. If I hover over this, it tells you that there's an overload signal at the output. That means that we're saturating the output because it doesn't match the range. So the 1 volt bias plus the 300 millivolt cannot be applied to the output. If I go to the output signal, you look at it, it becomes obvious. Why? Because we're sitting on the 1 volt range. So 1 volt, you have a 1 volt of bias, 300 millivolt is already above that. So of course we've saturated the whole thing and that's not going to work. Now I can go ahead and adjust that by not allowing it to set it automatically and then go over here and set it to 10 volt. And as soon as I do that, everything settles back down. And if you look over here, it tells you that the signal used to be overloaded but not anymore. So I can clear it and everything goes away and now we're back to normal operation. Now if I look at the actual value, it shouldn't have made a difference, and indeed it hasn't. It's still a 1.19 because 1 volt is too small to make a difference anyway, but the bias voltage now indeed shows up over here. So you can now begin to understand how this whole system works together and the interconnect between everything, but it's all available to you to change on the spot. So I've changed the component again. Now we're looking at a 2.2 microfarad electrolytic capacitor. Now this is going to be subject to resonance much more than the tiny capacitor we were looking at before. In fact, you can see at 100 kilohertz, we're already sitting at minus 23 degree. And of course, the value of the capacitance no longer makes any sense because we are now close to its self-resonance frequency. Now it's going to be hard to find this by just playing around with the oscillation frequency. The natural thing to do is to plot it as a function of some kind of a sweep. And the sweeping functions of this instrument are incredible. You can pretty much sweep anything versus anything. So let's try this out. So we have two plots over here, plot number 1 and plot number 2, and we can drop what we want to show on them. So at the top plot, let's plot the capacitance because we can see its change of value across frequency, and we can plot the phase at the bottom one. So over here, if I look at this, the CS series capacitance is parameter 2 in the impedance analyzer, and therefore parameter 2 in the impedance analyzer is going to be the capacitance. We can add that and it will add it over here. This is using the series capacitance as parameter 1, but now it's measuring it versus the series resistance. But I don't really want the series resistance, so I can just drag it and get rid of it. I do actually want to plot the phase, and that is the impedance analyzer phase as a function of the impedance there. We're going to plot that as well. Now we have both of these parameters, and we can define our sweep. We can sweep from 100 hertz to 5 megahertz in this case. That should be plenty to see the change in the capacitance and phase as a function of frequency. 100 points in a logarithmic fashion. That all looks great. Well, we can go ahead and run a single sweep and see what happens. There you go. And as soon as you press that, it's going to tell you how long this sweep is going to take in total. At the beginning, it's going to go through some auto ranging, and once it settles down, it'll tell you the exact value. There you go. A few seconds is nothing. And as we can see that the correct characteristic of the capacitor is now plotted as a function of frequency, which is fantastic. We'll wait for it to finish, and then we can analyze the plot. So in this case, I don't really care about the vertical cursors. I can go ahead and turn those off. And now I can see how the capacitance has changed across frequency. So this cursor at the very top is around 100 kilohertz or so. You can see the value is 2.15 microfarad, which makes sense because we're low enough in frequency. We have a pretty good capacitor there. But at around 5 megahertz or so, it has dropped to 222 nanofarad. So we're almost at the edge of the inductive behavior of this component. We're no longer really a capacitor. And a similar story with the phase. In a phase at really low frequencies is essentially minus 90. And at higher frequencies, we're at minus 5.1. Again, we're getting out of that negative phase, which is a characteristic of a capacitor. And you can now export this. You can export it as image. You can export it as MATLAB compatible files. There's really no end to that. And you can see all the buttons for storing. You can also have automatically adjusting the axis, everything you would expect from a nice plotter. If you go under math, you can also add a whole bunch of custom math on top of this so that you can extract higher order parameters as you want. I mean, you can get more and more complicated. There's also a history here. So every time you run this, so for example, if I do another run, it's going to run exactly the same thing because I haven't changed anything. And these points should land exactly on top of the old plot. and as you can see it, the old one changes color, and you can see we're tracing along the path again, so the measurement is extremely repeatable. And then now you have a complete history over here, and you can keep erasing histories or getting rid of ones that you don't like and maintaining exactly what has changed through your setup. So they clearly thought about this. And because we're measuring impedances, we can measure other things like filters, in particular ceramic filters with very high quality factor, because we have precise control over our frequency step, so we can catch the center frequency. So here I have a ceramic filter right over here connected at the input of our instrument, and we can do a sweep on and see if we can catch the center frequency. Now I happen to know that it should be around 455 kilohertz, so I've limited the sweep from 450 to 460 kilohertz. Let's see what it does. We'll do a quick single sweep over here. Now this is a band pass filter, so we expect the impedance to be quite high at the beginning and drop rapidly and be at this minimum point right where the resonance is. So let's see if that happens. You can see that it's dropping. There it is. We've hit a minimum over here, so we'll wait for the sweep to continue until it is done, and we can see if the center frequency is correct. There we go. It's completed. So let me bring this over here and check it out, 455 kilohertz, exactly where you should be, and the impedance has reached its minimum value. So if I put the measurement over here, you can see we're at 281 ohms, whereas at the beginning, just a few kilohertz away, we're now 10 to 20 times higher. So it's a very, very high quality filter. At the same time, the phase crosses its 0 point right at the center of the bandpass. So all of that makes perfect sense. But some of these filters can behave quite unusual just outside of their frequency range. So we can extend that to, let's say, 475 kilohertz, just a little bit above, and do another sweep while keeping this one on the display. So at the beginning, we're going to roughly overlap this. The frequencies are not going to line up exactly, but it doesn't matter. The shape is going to be the same. Here we go. So we're going through the same thing, but now we're going to extend beyond the range we did our initial measurement, and look at what happens. Look, we do have this weird effect, and the phase crosses once again, and we even have a second resonance point. So sometimes it's very helpful to measure things above and just even close to where you're measuring it, because it can have really unusual effects, especially for things with very high quality factor. So this impedance sweep is super helpful. So let's do some semiconductor analysis. What I have here is an NMOS transistor, but I have shorted the source and the drain together, essentially turning a 3-terminal device into a 2-terminal device. And now we can measure the capacitance between the gate and the combination of the source and the drain together. Basically, I have created a varactor, but it's not like a varactor that's sitting in an N-well. It's an NMOS transistor turned into a varactor. At the same time, there is an ESD protection diode that sits between the gate and the source. So that's another degree of complexity, because it will have its own characteristic and capacitance. What I want to measure is the CV characteristic of this device, basically capacitance as a function of voltage across the 2 terminals, just like you would measure in a varactor. And that's exactly what I have done. In fact, I have added it right over here in front of the device, connected it to one of the PCBs, so now we can measure across it. But I do need to now sweep the voltage across it, which means I have to sweep the bias voltage, which we already know is pretty easy to do. I have set that up over here. It's an offset voltage going from minus 5 volt to plus 5 volt. That allows me to bring the transistor through all of its regions of operation. And I had to make some adjustments. For example, I had to make sure the output range is at 10 volts. I'm making a 2-terminal measurement because the input voltage measurement of the device is limited to 3 volts, and 5 is of course more than that. And I've enabled the bias voltage. Everything else is pretty much the same. All right, let's see what happens here. There you go. So it's going to run through all the bias voltages. I have fixed the input range of the current measurement to 1 milliamp. It will make it a little bit faster because it doesn't have to go through auto ranging and everything else. There we go. It's almost finished. And we see a very familiar curve. This is exactly what you would expect to see. You go through accumulation mode, depletion mode, and inversion mode, and the capacitance changes accordingly depending on those 3 states. Now, interestingly enough, the slope here going from depletion to inversion isn't as sharp as I thought, and perhaps part of that is because of the ESD diode that's inside of it. But if you look at this carefully, you may already say, well, there's something weird going on here, because this is an NMOS transistor. So you would expect the lowest point of the capacitance in the depletion to happen at the threshold voltage. The threshold voltage is 0.5 volts approximately, but this is happening at minus 0.5 volt. Well, I'm sure by now you have figured out why that is, and that's because this is put in upside down. We have to apply the voltage in the other direction, and the easiest way to fix that is to just unplug it and plug it back upside down. And we can run exactly the same sweep, and that should, in theory, correct this issue. Let's give it a try. The old one stays there, of course, and you can see that it's already a little bit different. So hopefully it's going to come down and cross right around here. And there it is, look at that. How cool is that? That's exactly how the theory predicts this should behave. So I can now put that over here, and I can measure the threshold of the device through its CV characteristic at the lowest point of the depletion. I can also measure the minimum and maximum capacitance this device can give us. So the lowest point of capacitance is around 672 picofarad, and the highest point is around, if I can grab this, around 900 or so. I think there's something wrong with my mouse a little bit here. There you go, 954 picofarad. Yeah, this all looks really good, and how easy it is to set this up and run right through it. Now at the same time, again, you can export this and take it into a different piece of software and analyze it further. But in a couple of clicks, we have a full CV characteristic. So now let's capture some environmental effects on the value of some electrolytic capacitor. So here I have connected with 4-wire an electrolytic capacitor that sits into the chamber of this temperature controller. That capacitor looks something like this. The one in here is 100 microfarad, and right now we're sitting at 25 degrees Celsius. What I want to do is cool it down all the way down to around minus 20 Celsius and see how the value of that capacitor changes, because electrolytic capacitors are not very good at low temperatures. They're also not great at very high temperatures, but cooling it should be pretty interesting. We should be able to capture a whole bunch of trend effects directly on this instrument as this thing cools down. Let's take a look. And for that, we're going to take advantage of the plotter function. So the plotter gives you any parameter you want as a function of time on a wide range of scales. Right now, I'm looking only at a 2-second scale so you can see all the data pass by. We're measuring this capacitor at 25 Hertz, so fairly deep into its operation frequency, and we're sitting at 111 microfarad. The series resistance is 1.6 ohm, which is to be expected for a capacitor like this, and everything looks good. This is how the LCR would run normally. Of course, because you have complete control over the GUI, you could run your own loops and submit temperature and measure and correlate it from the outside so you can have a proper temperature correlated measurement. In this case, we just want to see the trend. We're not reading any direct measurement from the temperature controller. So I'm going to set it to minus 25 and click start, but at the same time, I'm going to change that. So we're looking at, let's say, a 5-minute range over here. There you go. So here we're seeing the value of the series resistor and capacitance, and at the bottom we're looking at the average. So you have a whole trend section here. You can plot histogram, averages, whatever you want. So the number of sophisticated plots just compounds on top of each other. Let's go and turn the controller on and see what happens. So we've been running for a few minutes now. The temperature is just below 0 Celsius. And look at that. We're seeing a decrease in the total capacitance going down, and we see an increase in the equivalent series resistance. One thing I wish these plots had is that if they could split the y-axis into two, so that whenever you have two or more, you could assign some on the left axis and some on the right axis. Right now, if I want to see the value by clicking on that, the axis on the left, the vertical one, changes to show you the appropriate value, which works reasonably well, but sometimes having two axes also helps. So you can see the equivalent series resistance started from about 1.7, is already now to 2.3 ohms, and the capacitance started at around 111 microfarad, is now all the way down to just below 108.5. So this is normal. This is what happens to capacitance when you chill them. And of course, electrolytic capacitors in the cryogenic temperatures do not work at all. They completely break down. Now this is not going to get to those temperatures, but we can see the trend quite nicely. One of the other nice things is that you can set the trend to be a different time scale than the actual plot, so you can have a longer scale average as shown here. These are basically just the two averages of those two signals. Similarly, I can select them and the axis here changes. Yeah, it's really sophisticated. You can of course take this and close loop around it if you want to. Another thing I didn't mention earlier while this is running is that there is an entire confidence indicator here. If you enable the confidence indicator, sometimes when the measurement may not have a very good accuracy or reliability, it will label those and remove them from your data. And it's a huge help if you don't want to pollute your measurements, so you know what you're measuring is actually within the confidence of the instrument as well. A really nice feature. I haven't seen that in a lot of other instruments. So let it run a little bit more. I think I should be able to get down to minus 20 so we can see where it settles down. So I let the device come down to minus 15 Celsius and then cranked it up to plus 100 Celsius and see what happens to the capacitor during that huge temperature change. So at the lowest point, when the capacitor was the coldest, we reached 106 microfarad. And then after we reached plus 100 Celsius, it reached 121 microfarad. So that's a fairly wide range of capacitance change. At the same time, the ESR, of course, also changes with it. Now, one thing to note is that it takes a lot more time to cool down the capacitor, and you can see that slope is shallower than the slope the other way, and that has to do with the fact that these are Peltier coolers, so they don't have the efficiency in both directions. But this allows you to completely characterize the temperature effect, and if you have a closed loop, then it will be even more interesting because then you can plot the whole thing as a function of temperature. Now, because we have all these auxiliary inputs and auxiliary outputs, we can use some of the internal generators of the instrument and generate waveforms and apply them to external devices. And then we can use the instrument to measure those effects on those devices at the same time, essentially creating an all-in-one device that controls everything and measures everything. So you have to be imaginative to really use all these things that are built in. So inside of this instrument, there's something called a threshold unit. And from there, you can configure all kind of interesting thresholds. Here I've created one that just has an on and off state, each of them lasting 500 milliseconds. Basically, I'm generating a square wave, and that square wave can then be fed into the auxiliary ports. And if I go under the aux menu over here, you can see that I'm using that signal as an input, and I'm applying some offset and scaling, ultimately generating a signal coming out of the auxiliary, which goes between 0 and 2.75 volts. And because it is slow enough, I can actually see that happening right over here. You can see the auxiliary output 1 is jumping between 0 volts and 2.75 volts. Now I can use that to drive an LED, which I will show you when I show you the setup. Once I drive that LED, it will turn on and off. Now I will take that signal and feed it back into the auxiliary input at the same time so I can monitor it. And if you look over here, the auxiliary input 1 is also jumping between two values. It's jumping between 0 and 2.65. Now 2.65 is a little bit different than 2.75, and that's because we're driving an LED. And when that LED draws some current, the voltage will drop, so auxiliary input will digitize the reduction too. So you'll see the actual value. All of that kind of works together. I know it's a little bit complicated. You really do have to be imaginative to use this, but let me show you the setup. It will become clear what I'm trying to do. So the square wave generator is applied and scaled and is coming out of the auxiliary output. You can see that I'm splitting that signal into two and feeding it back into the instrument onto the auxiliary input so we can monitor it. At the same time, I'm driving this LED. So this LED is turning on and off at the rate of about 1 Hertz, which makes sense because we have a half a second on, half a second off situation. Now this LED is shining into an identical LED of its own kind, which I'm measuring the capacitance of. So what would happen in this case? Well, the photons leaving the LED will hit the junction of the other LED, and they're all roughly the same wavelength because they're of the same type, and with sufficient energy, it will create holes and recombination electrons inside of that junction, therefore changing the depletion of it. So you expect a tiny change of capacitance potentially arising because you're shining light back into the LED. This is going to be a pretty small value, but I'd like to see if we can capture that, and I'd like to see how fast the MFIA can actually show this result to us. So we're going to use the data acquisition toolkit inside of it to measure it. Let's see. So the whole thing has been running now, and if you look carefully, you can see that the parallel capacitance is indeed changing between two distinct values. And here I'm applying a reverse bias of 1 volt across the photodetector, which is really the LED I'm using as a photodetector, and therefore we should be able to capture this effect. Now you're not seeing any of the transitions. We need a data acquisition for that, and there is a data acquisition option with this instrument, and it can allow you to sample things pretty quickly so you can see the result of that, and that's under this tab. Now once you have this, it opens up a whole bunch of other things you can do. You can define what kind of signals you want to capture, how long you want to capture them, and not only that, you can actually trigger on various signals. It becomes pretty sophisticated. So I've really set it to capture 16 individual events at a threshold of 1.5 volt on the auxiliary input. So we should be able to now correlate these two measurements. I'm plotting the auxiliary input, and I'm also plotting impedance sample 1 parameter 2, which is the parallel capacitance. Let's do a single one. So it should capture a whole bunch of waveforms, and take a look. Here's the blue line, which is barely visible over here. That's the step. That's what turns the LED on. And if you look, when the LED turns on, the capacitance drops. And it takes a different trajectory each time to get there. But there is a very clear distinction between these values over here and these values over here, and it's completely repeatable. So indeed, we do have two different effects on the capacitance, and we can capture this pretty quickly. And you can even make capacitance measurements down into the tens of microseconds. In this case, we're looking at it in the millisecond scale. But if I do another set of capture, another 16, you can see that it would fill up this area. So the transition is somewhat unpredictable. I actually don't fully know why sometimes we have an overshoot and an undershoot and sometimes we don't. It may have to do with how the charge is distributed, but that would be an interesting thing to discuss in the comment section. But there's definitely two distinct values of the capacitance that we can catch here. It's amazing. Just think about how complex this is and what we are trying to analyze at the same time in one box, but definitely with the software, it is possible. Now you may ask, how do we know this is because of the photons and the light and it's not because of some weird EM effect across the two diodes? Well, it's simple. I can block the light using a piece of plastic which does not block any of the other EM fields, and we can see if it's going away. Right now I'm making a continuous measurement. So there you go. I'm going to put a piece of plastic here in between, blocking the light, like so. And look at that. The effect is essentially gone. So now it's going to stabilize somewhere down the middle after a while because there's no light being applied to it anymore. But yeah, that effect certainly is correlated with the photons arriving at the other light. There it is. You should start bunching up here in the middle. Pretty cool effect. So far we've been looking at the impedance analyzer, and to say that we haven't even scratched the surface would be an understatement, because underneath all of this is still a lock-in amplifier, and a pretty powerful one with a lot of different features that you can add on top of that. So let's take a look at it a little bit. This review definitely has to be split into two videos because there's so many other cool things that I want to do with the lock-in amplifier, the PID controller, and the modulation and everything else you can do, but at least we should do a little bit with it so we can see what's going on. So here's the lock-in amplifier menu. You can see that in this particular one, the option is enabled and we have 4 of them. So there's a lot you can do. Some of the basic settings still control the input and output voltage amplifiers as well as the drivers. So that's in a sense very similar to the impedance analyzer because the impedance analyzer was just running on top of this to begin with. If I click over here, you can see the beautiful block diagram of the lock-in amplifier, and it looks really familiar. This is what we talked about at the very beginning of the video, and you can see the entire signal flow, what is connected to what. Now in this case, we were using the impedance analyzer, so you can see the front end is configured as a current input. So the current input comes in, goes into the transimpedance amplifier, and there's scaling and then mixing and everything else that follows. I can change that and make it a signal in, and immediately we get a differential input, which you can float or make it single-ended, make it 50 ohm terminated, make it AC coupled. It's just so many things you can adjust. And this signal flow is super helpful because we can see exactly what is coming from where. You can add outputs from different places. We can see which output is arriving to the actual driver. You have all these references and different PLLs, 4 of them that you can control independently. This is a full-fledged, sophisticated and complex lock-in amplifier on its own. We should do at least one experiment with it so we can see how it works. Now, one thing I wish they did is that at the bottom here, they show when something is overloaded. It would be nice if it showed up here a little bit more. For example, the block can become red, so you know what's going on with regard to the input and output. It's a minor change. I think it would go really a long way. So let's think of something simple to do, just so we can see it work. So here's our setup. Let's try and see if we can do some quasi-radar experiment using some ultrasound modules. So the setup itself isn't that complicated. We have the drive signal coming from the lock-in amplifier driving one of these ultrasound modules. That's going to create sound waves at the frequency that is coming in, and it's going to bounce around various things around the room. And then when it bounces back, it's going to be caught by an identical ultrasound module, which is sensitive to the same frequency, and that's going to create a voltage that is read back by the lock-in amplifier. So in a sense, the signal driving the ultrasound and signal coming back are coherent in frequency and in phase. So any deviation from that can be easily detected with the down converters inside of the lock-in amplifier. But we wanted to do something a bit more sophisticated than that. So in front of this, I have a speaker. Now this speaker can be driven from an arbitrary waveform generator, and I'm using the Roden Shores MSO4 series right there to directly drive that. So think about what happens. When I drive this speaker, the diaphragm of the speaker is going to move back and forth ever so slightly. And that movement, that displacement, is going to cause a phase and a frequency shift directly on the signal reflected off the surface. And that's going to be detected by the ultrasound modules. So it's kind of like a radar. But you have to be careful not to confuse that we're not detecting the sound waves coming out of this, because this is going to run at 100 hertz, very low frequency. But this is running at 25 kilohertz. So we're not measuring the sound, we're measuring the displacement of the diaphragm of the speaker, a mechanical feature, a completely different thing. So it's an unusual but a very interesting setup. It's going to become clear when we run it. If the speaker is not running, the signal is bouncing back and forth. It's just going to be determined by this distance. So you're going to get some phase offset, and the lock-in amplifier should be able to easily detect that. But it will become very interesting when we turn this on. And at the same time, I'm taking the auxiliary outputs 1 and 2 of the lock-in amplifier, and I can configure them to output various things from the down converter signal, so we can look at them directly onto the oscilloscope as well. This can be helpful in some situations when you have an external digitizer, you want to make some measurements using a different instrument. But of course, the lock-in amplifier itself has internal digitizers, so we should be able to look at that anyway. But I thought it would be cool to see how we can reroute signals and measure them using an outside instrument too. So let's see if any of these measurements make any sense. So I have the output set to 25 kilohertz on the first harmonic, and that is going to be the standard frequency of the ultrasound module. I'm driving it with a 6-volt peak-to-peak signal, which is pretty strong, so a lot of ultrasound coming out, and it's a single-ended signal at the output, which makes sense because these are single-ended ultrasound modules. On the return path, I'm doing exactly the opposite. I'm looking at a single-ended signal coming in. The range is 300 millivolts, so I don't saturate the input, no particular scaling, but that signal is going to now mix with the actual oscillator frequency because everything is coherent. I have an 8-order filter with 400 hertz of bandwidth on that. We will see why in a second. And then I can reroute any of my measured signals into the auxiliary ports. So here I am routing X into the auxiliary port 1, and I am routing Y into the auxiliary port 2. You can also use auxiliary port 3 and 4, which are the phase and the radius, but I'm not using them in this setup. You can also set that, of course, in the auxiliary port in exactly the same way. You can scale them as you see fit. So a lot of flexibility is to be expected. But does this actually make any sense? Well, we can easily find out by putting our hands in front of it. Right now, the speaker is in the front, so the signal is bouncing back and coming there, and we're measuring it, a phase of 108 degrees and a 71 millivolt RMS signal coming in. But if I put my hand in front of it, as I move my hand slowly toward the ultrasound, this phase should wrap around very quickly because the distance is comparable to the actual wavelength of sound in free space. So let's try that. I'm going to put my hand in front of it. And if I slowly bring my hand, you can see that the phase is rapidly rotating around, and the amplitude, of course, is going to change because it's not bouncing perfectly off my hand. But yeah, you can see it is actually doing exactly what it's supposed to. So that's exciting. But what does the signal actually look like? Well, the signal is arriving at the ultrasound is always going to be a sinusoid. So I can look at it in the scope because this has a built-in scope over here, and it can trigger things and anything just like a regular oscilloscope would be. We're sampling at 60 megahertz. So here's a sinusoid coming back from the ultrasound at 25 kilohertz. Well, if I put my hand in front of it, not much is going to happen. You will see some amplitude change, but of course we're triggering on this signal, so you're not going to see any phase change. But if you look at the plotter, here I'm plotting two values. One is the X, one is the Y. Remember, those are these signals coming back from the demodulator. If I bring my hand in front of it, and if I gently move my hand, let me put the camera back on so you can see correlation there. And look at that. Put my hand in, and if I gently move it back and forth, you can create your own little sinusoid. This tells you that the phase is wrapping around. If I move quickly, you can see that it's going to be all over the place. But yeah, isn't that cool? You can actually measure the exact distance of my hand. So it's very sensitive. So now if I move the diaphragm of the speaker back and forth, it's the equivalent of me moving my hand back and forth. The signature is much smaller, but we should actually be able to detect this movement using this quasi radar that we have going on. Now, because the sound waves are bouncing all over, me just moving in my chair sitting near the setup is going to create some sway. So everything is mixed together, as you would expect, because all these interference of sound constructively and destructively will have some effect on the return signal. So let's apply some sinusoid or some signal directly to our speaker, which I can do using the remote display of the oscilloscope. So if I go under the generator, I'm using generator 1 over here, and I can apply a sinusoid. So here I'm applying 125 hertz to it, but I can change that. Let's apply just 1 hertz because 1 hertz is going to be a little bit easier to visualize. We can go in and enable that. And as soon as you do that, you can see the signal is moving up and down because the diaphragm of the speaker is moving up and down. These are the X and Y signals that we are simultaneously monitoring on the oscilloscope. But if I go back over here, look at that. That's our 1 hertz signal. That's the actual physical movement of the diaphragm of the speaker being caught with the ultrasound reflection, which is really cool to see. Satisfying little experiment. Now we can make that faster. So if I go back over here and put that now to 125 hertz, there you go. These are two sinusoids, so X and Y. There's a lot of things you can note about this right away. First of all, they're not perfectly linear because we're driving the speaker really, really hard to get that movement. And the reason I chose 125 hertz and not anything louder is because the sound is going to be super annoying. 125 is not that audible. Maybe you can hear it in the background right now. There you go. Now you can see the signals are obviously moving much, much faster. But you can take this whole thing a step further and look at the spectrum of the return signal. Now it is much more interesting. And here's the spectrum, and we can measure it live and see the heat map and everything on there. So let me clear the history here, and then let's see if it makes any sense. So we're looking at a 4 kilohertz span, but I'm limiting my field of view to only 400 hertz because the ultrasound modules don't have a lot of bandwidth anyway. So we're looking at multiple things at the same time. We have phase and frequency modulation on top of the signal coming back into the ultrasound like a radar would. And there's, of course, Doppler effects and everything on top of that. So if I put over this marker here, you can see that it is at 125 hertz. And there should be the image of it on the other side. And that is also there, 125 hertz. And look, the second harmonic of that signal is also present because of the nonlinearities that are coming from the speaker. Think about everything that's being measured here. By the way, this is just me moving around because I talk with my hands a lot. And you can see the noise from moving around, that's just signal bouncing off of me. But the most dominant tones are the tones that we're directly applying. I find this to be such a cool little experiment because it demonstrates not just the Doppler effect and all the other things, but it also shows you how a lock-in amplifier works. Now, if you go ahead and put a modulation on top of it, these tones would move along with the modulation. So let's try that. You can go over here. We can go under the modulation tab here, and I have created an FM modulation, a very slow one that moves at 100 millihertz, but it has a pretty big depth, 100 hertz of deviation. So let's turn it on, and look at that. And this is the actual movement you're capturing. We're looking at the movement of the surface of the speaker. And then as it goes back and forth, it's being caught by this. And the signal here is widened because of the way the sampling is working, of course. I think this is super interesting to see that it works. Now, one thing you need to watch out for in this particular lock-in amplifier that's a little bit different than the other ones is that this phase shifter of oscillator 1 sits in the same path as the demodulator as well as the output driver. Normally, you would expect this to be sitting here or here, because if I change this phase, nothing's going to happen because they experience both at the same time. So if you want to adjust the phase of the oscillator and see the effect, you'd have to use a different oscillator. It's a little bit confusing. If you've used other lock-in amplifiers, they do this a little bit differently. But I hope that this gives you some idea of how many complicated things you can add under the roof in the same setup in the Lab 1. And that's why I want to do another video showing all the other complex things you can do, especially the PID controller. You can wrap an entire controller around this in the digital domain. Very interesting stuff. So Zurich Instruments has been acquired by Rohde & Schwarz, and as a result, all their equipments will now be part of the Rohde & Schwarz ecosystem. I'm curious how they will embed and combine them, but I do hope that they allow Zurich Instruments a certain autonomy because of the great Lab 1 platform and all the instruments that work well together. So we have signal generators and quantum analyzers. They're very much focused in this space. Qubit controllers, as you can see. But if you go further down the list, there's arbitrary waveform generators that can go up to 144 channels, again, for quantum applications. And then down at the very bottom of the list, we see lock-in amplifiers going all the way up to 8.5 gigahertz. I'd love to get my hand on one of these. Imagine the kind of experiments you can do in the RF domain, especially again for quantum computers at these higher frequencies. And if you go all the way down, we see, of course, the MFLI and the MFIA. The LI is the lock-in amplifier version, but really underneath, they're essentially the same kind of instrument. So there's a lot here, and I'm curious to see how they evolve their instrumentation now that they're under Rohde & Schwarz. And there you have it. I hope you enjoyed this extensive review of the MFIA. There's a lot more still to say, and hopefully I'll make follow-up videos where we can do other kinds of experiments with its many features that are built in. Let me know in the comment section what you think about it. As I said, these are long videos with a lot of efforts that go into them, so your feedback is always appreciated. See you next time.